Hey guys, we're back with part 3 for chemistry paper 2H from May 2008. So let's pick up where we left off. Alright, so question 7a says that magnesium chloride is a soluble salt that can be made by reacting magnesium carbonate with hydrochloric acid. So magnesium carbonate is an insoluble in water, meaning it's a solid. So here we have some magnesium carbonate. We add it to this HCl over here, and we give it a bit of time, and we have some magnesium chloride in there, so Cl2. Alright, so it is magnesium chloride. This is soluble in water. So you have to figure out how you can take a dry sample of magnesium chloride crystals from this solution over here. So first of all, magnesium carbonate plus hydrochloric acid gives us magnesium chloride. And if you probably know your reactions of acid with carbonate gives you the salt, it gives you carbon dioxide, and it gives you water. So the carbon dioxide will probably be released into the atmosphere in this solution. Okay, so that's out of the picture. So what we have in the solution is basically a solution of magnesium chloride in water, which is just an aqueous solution of magnesium chloride. So we have to just separate that. Now note that the salt and the water are not chemically bonded together, they are just physically bonded together, meaning we can use physical methods of separation. So first of all, we have to figure out a way to get rid of all of this water, because that's not what we want. We want the magnesium chloride, alright? But the magnesium chloride is kind of a part of the water, their solution. So how would we do that? So first of all, we would probably have to heat the water. Oh, sorry, let me start from the beginning. I missed out a few bits of this answer. So they said, describe how you can make a dry sample of magnesium chloride crystals from magnesium carbonate and dilute hydrochloric acid. So I kind of explained it earlier. So you need to start off with the magnesium chloride crystals, right? The magnesium carbonate, which you have. And you need to add that to dilute hydrochloric acid. So if you add that to dilute hydrochloric acid in here, you're going to get magnesium chloride with a bit of water. So an aqueous solution of magnesium chloride. So the first step is to add the magnesium carbonate to the acid. Okay? So we get this solution initially. And then we have to stir it, obviously, because we have to mix it. Because these are solid particles. They're not just going to dissolve. We need all of it to dissolve. So we've got to stir and mix the solution. Stir or mix the solution for a bit, and then what you want to do as well is you want to make sure that you add excess of this. Now the reason for adding excess is because these are solid particles, right? So if you add excess, you can be 100% sure that all of the HCl has gone away. And you can always filter out solid particles. Solid particles are very easy to filter out. It's a very simple way of filtering. And so you can always be sure that you can always filter this out. However, if you had excess HCl, you couldn't filter that out because you don't know what is HCl and what is the magnesium chloride solution. So that's why you have to always add excess carbonate. So over here you'd probably mention that you have to add excess magnesium carbonate. So add excess magnesium carbonate to the acid and keep stirring and mixing while you do so. Okay? Now since we've added excess magnesium carbonate, right, we will probably have excess, like small bits of carbonate in this solution, right? Because we've added excess. Not all of it has reacted. So what we do is then we add it to a filter. I think you guys know what this is. So you take the filter paper and then you pour the solution. You pour the solution inside and then you'll get just the liquid. So you get rid of all the solid over here. Right? So we just say that we filter the solution. Right? The solution with a few solids, yeah? And then now we're left off with MgCl2 solution with water. And these are the only two things left in the solution. No solid, no nothing. Okay? And we're sure that it's just MgCl2 and no HCl because we added excess of magnesium carbonate. Then what we got to do is, how do we get rid of this water? Because we want just the MgCl2. Well, salts, as you know, probably don't evaporate, right? Because they're solids. whereas and they have high evaporation points or boiling points, sorry. Whereas liquids like water evaporate or boil at much lower temperatures. So we need to get rid of this water. So what we do is we heat the solution. And we'd heat the solution to get rid of the water. Okay, like you can say this in other words, but basically what the concept is, you heat the solution to get rid of the water and evaporate the water. To evaporate the water, that would even be a better word. And what you'll be left with is these small little crystals. Now they're really moist. So after all of this evaporation here, okay, sorry if it's a bit messy, you'll be left with these really small, tiny crystals, yeah? And it'll be a little bit wet, yeah? So what you want to do is you don't want to evaporate all of the water. You want to evaporate some of it, but just leave a little bit. And then after that, you leave it in an oven to dry. So leave on a filter paper or on any paper in an oven to dry, because then you'll get the big crystals. And this is a more complicated concept. It's to do with the fact that they'll align themselves when they have more over a longer period of time, and if they have, I don't know, it's like a complicated concept. It's hard to explain. But in order to get big crystals, you have to leave a little bit of water, so evaporate most of the water, leave a little bit, and use those. Take that small bit and just leave it in an oven on any kind of thing, on any like surface or something to dry, and you'll get big crystals. So that's basically the process. So what you do is you add excess magnesium carbonate to hydrochloric acid, you stir it, right? Then you filter it to get rid of the solid, then you evaporate the water out, and then you leave, not all of the water, you leave some of it, and then you leave it out to dry in an oven or something like that, so you get big crystals. Question 7b says that 25 centimeter cube of sulfuric acid is placed in a conical flask, and a few drops of phenolphthalein are added, and the acid requires a certain amount for neutralization, and the chemical reaction is shown below. So they say, what color change is seen when the acid is neutralized? Now, phenolphthalein is another indicator, like one we encountered before in this paper, like litmus. However, it just has different colors in acid and basic solution. So in acid, phenolphthalein is colorless, whereas in basic solution, it'll be a pinkish or violet color. And in neutral solutions, phenolphthalein is actually a pink color. Like this is more pinkish violetish, so it's a darker kind of thing. So when an acid is neutralized, what basically happens is that all of the acid, so you have a little bit of acid here, you add base, and remember when you add acid plus base, it forms salt and water. So eventually you'll start off with this amount of acid, let's say, okay? Then you add a bit of base. This amount of acid will be eliminated. Then you keep adding base until all of the acid is eliminated. All of the base is obviously eliminated, the acid, and all you're left with is salt and water, which is neutral. So that means that initially we had all the acid and we had the phenolphthalein in the acid. So it means that the color of the solution was colorless. But then after we've added all of the base and neutralized all of the acid, we're left with neutral salts and water, meaning that the phenolphthalein will be pink. So changes in color from colorless to pink. Alright, so question 7b2 is asking you to calculate the amount in moles of sodium hydroxide used. So we don't know what the number of moles. But what do we have? If you look at the question, we have the fact that 8.7 centimeter cube of sodium hydroxide is used, so we have the volume, and we also have the concentration of sodium hydroxide used. So using this triangle here, we don't have the number of moles, we have the concentration and the volume, and from this we know that number of moles equals concentration times volume. So number of moles of NaOH equals concentration of NaOH times volume of NaOH. So in this case, it'll be number of moles equals concentration, which is 0.150, right, times the volume. Now the volume over here is in centimeter cube, but we need to convert it into decimeter cube because the concentration is in moles per decimeter cube, not in moles per centimeter cube. So we have to convert centimeter cube to decimeter cube. And the way you do that is you divide centimeter cube by 1,000. Right? And then this is the amount in decimeter cube. So you just do 8.7 divided by 1,000, and that'll give you your answer, which is 0.00131 moles. Okay, so question 7b3 is asking you to calculate the amount of moles of sulfuric acid used. Now how do we find out the number of moles of this used? So from the previous question, we figured out the number of moles of NaOH used. And we assumed that the number of moles of NaOH used completely neutralized all of this acid. Okay? So that means that 0.00131 moles of NaOH neutralized the acid. Now from your chemistry class, you should remember that all reactions happen in certain mole ratios. And these mole ratios are determined by their chemical reaction. So like the chemical reaction happening here is shown over here. So these mole ratios occur in these chemical reactions. So in this case, 1 mole of H2SO4 reacts with 2 moles of NaOH to form 1 mole of Na2SO4 and 2 moles of H2O. Right? So all reactions happen in that process. So if we used 0.00131 moles of NaOH, right? And if 2 moles of NaOH react with 1 mole of H2SO4, I'm going to use a ratio. So see, that's a ratio. So if 2 moles of NaOH react with 1 mole of H2SO4, how many moles of H2SO4 react with 0.00131 moles of NaOH? So we'll put that as X. How many moles of H2SO4 react? So that means we can say that these ratios should be equal. So 2 over 1 should be equal to 0.00131 over X, right? So it means that X, which is the amount of moles of H2SO4 reacting, should be equal to 0.00131 divided by 2. So that means that the amount in moles of H2SO4 reacting with NaOH is just 0.00131 divided by 2, which is 0.000653 moles. So it means that much of H2SO4 reacted. And so that is the amount of sulfuric acid used. Now question 7b4 is asking you to calculate the concentration in mole per dm cube of the sulfuric acid. So how do we find out the concentration? So basically what we have is we have the number of moles of sulfuric acid used, which we found in the previous question, and we also have the volume of sulfuric acid, which is 25 centimeter cube. So now we don't have the concentration, but we do have the number of moles in volume. So the equation is as follows: just concentration equals number of moles divided by volume. Remember, you put your finger over the concentration, because that's what you don't have, and then you're left with number of moles over volume. So that's how that triangle works. So concentration of sulfuric acid equals the number of moles of sulfuric acid over the volume of sulfuric acid. So now the concentration equals the number of moles we found out earlier was 0.00 I think 30653, right? That's in moles, and the volume, as it says in the question, is 25 centimeter cube, but we need it in moles per decimeter cube, right? So it means that we need to convert this 25 centimeter cube into decimeter cube, and we've done this before. All you got to do is divide by 1,000. So you divide this by 25 over 1,000, and what you will get is that the concentration of H2SO4 is 0.00131 0.261 moles per decimeter cube. And that is your answer. Alright, so question 8 says a student notices a white solid around the top of a bottle of dilute sodium hydroxide. So there's a little bit of white solid on the top of the bottle. Let's just say this is it. And she suspects that it's sodium carbonate, so Na2CO3, sorry. Describe the test and the positive result expected if that she can do to see if the solid is a carbonate. So she wants to test whether it's a carbonate or not. So she wants to test basically for the carbonate ion, right? And if you refer to your ions and if you try to recall your ions, test for ions and gases, you'll recall that the test for carbonate ions is to add the carbonate to an acid. So you add the carbonate to an acid. So you take some of this solid, you add it into an acid, let's just say HCl. And if you remember your reactions of carbonate with acid gives carbon dioxide, water, and a salt. Now, if we take that carbon dioxide, so we'll first of all, if we add the acid, we'll see that there's fizzing and bubbling because carbon dioxide is formed. But if we take that carbon dioxide and put it into lime water, remember, carbon dioxide turns lime water milky. So the test for this, to see whether this solid is a carbonate, is you add the carbonate to an acid, right? And you collect the gas produced and add it to lime water, which will turn milky. So that is the test, and that's a positive result. So the test is to add the carbonate to the acid, and the positive result is the gas produced will turn the lime water milky. So 882 says that carbon dioxide reacts with sodium hydroxide solution to form sodium carbonate and water. So you just have to write a chemical equation for this reaction. So carbon dioxide, simple, CO2, very common, and that reacts with sodium hydroxide. I'm hoping you guys know, so sodium is Na, hydroxide is OH, right? And that gives you sodium carbonate. I'm just going to make this should be a pretty straightforward question. Sodium carbonate and water. So that's H2O. So now all you have to do is balance this, and if you guys have any questions about how I derived these formulas, just post below because I've already covered it earlier. So, okay, you just have to balance this equation. So first of all, we got to balance the NAs. So we'll add a 2 here to balance the NAs. And now we have to actually balance the H's. So, oh no, actually after I put that, it's all balanced because the carbons are equal, 1 carbon, 1 carbon, 2 plus 2 oxygens, and that's 1 plus 3, so that's 4 oxygens. There's 2 hydrogens and 2 hydrogens, remember? And there's 2 NAs, so that means this is balanced. So this is the equation. CO2 plus 2 NaOH gives Na2CO3 plus H2O. Question 8b says that air is passed through lime water in the apparatus shown below, and after a few minutes in this apparatus, this one, the lime water becomes milky, okay? Fine. Then the experiment is repeated using this, right, this following apparatus, and they're asking you what happens to the lime water after a few minutes, and you have to explain. So first of all, we know that the air being bubbled in is carbon dioxide, because carbon dioxide, the test for carbon dioxide is that it turns lime water milky. So that means that we know that the air in is carbon dioxide. Now, the second bit, okay, it's first the air is passed through sodium hydroxide. So carbon dioxide is added to sodium hydroxide, right? And then this is whatever is left is passed through and put into lime water. Now you have to figure out what's going to happen to this lime water. So if you look at the previous question, which is 8A2, we figured out that carbon dioxide reacts with sodium hydroxide solution, right? So that means that if we put all of this carbon dioxide solution into sodium hydroxide, all of the carbon dioxide is going to react, meaning there's not going to be any more carbon dioxide to go through there and into the lime water to turn it milky. So that means that there will be no change in the lime water, right? And the reason for this in lime water, whatever. And the reason for this is that the carbon dioxide reacted with sodium hydroxide to form, obviously, sodium carbonate and the other thing, which was, I forgot, wait, let me just check, which was water. Okay, question 8c says that 4.2 grams of sodium, they say sodium carbonate can also be formed in another way by heating this, sodium hydrogen carbonate, and they say that 4.2 grams of sodium hydrogen carbonate is heated until it's fully decomposed. Now they're asking you to calculate the amount of moles in moles of sodium hydrogen carbonate used. So this. Okay, so we don't know the amount in moles, so that's a question. Okay, but we do know the mass of sodium hydrogen carbonate, which is 4.2 grams. Now, something we always know when we have the chemical formula of anything, we always know its molar mass. And I'm guessing you guys know what molar mass is. It's just the addition of all the masses of each of the atoms, okay? So we can find the molar mass very easily. So, and then there's that equation that the number of moles equals the mass of the thing over the molar mass. So that's the equation. And the triangle is N, M, and M. That's the triangle. So we have the number of moles, so it's mass over molar mass. Okay? So the number of moles of sodium hydrogen carbonate is equal to the mass of sodium hydrogen carbonate, which is 4.2 grams, divided by the molar mass. Now, how do we find the molar mass? So the molar mass is found by adding all of the masses of the individual atoms in the compound. So we have one atom of Na. So we have the mass of Na, which is 23, and then we have one hydrogen, which has a mass of 1, right? And then we have one carbon, which has a mass of 12, and then we have 3 oxygens, which have a mass of 16, so 3 times 16. And so that'll give you a total molar mass for the compound. The total molar mass will be 84. And remember that molar masses on the periodic table are always given in grams per mole. So grams per mole. Yeah. So divided by 84, and that'll give you a number of moles of 0.05 mole. Question 8c2 is asking you to calculate the amount of moles of carbon dioxide formed. Now again, this is similar to the previous question. I'll just repeat it kind of. So all reactions happen in certain mole ratios. So in this case, 2 moles of sodium hydrogen carbonate is decomposing to give you 1 mole of sodium carbonate and 1 mole of hydrogen water and 1 mole of carbon dioxide. So if 2 moles of sodium hydrogen carbonate give you 1 mole of carbon dioxide, how much do 0.05 moles of sodium hydrogen carbonate give you? So we call that X. So it means that these two ratios should be equal, right? And that means that X, which is the number of moles of carbon dioxide produced, should be equal to 0.05 divided by 2, which is simply 0.025 moles. So 0.025 moles of carbon dioxide is formed. Alright, so they ask you to calculate the volume in the 8C3. They ask you to calculate the volume in decimeter cube measured at room temperature and pressure of carbon dioxide formed. And we have, they say that the volume of 1 mole of any gas's room temperature and pressure is 24 decimeter cube. So we have the number of moles, correct, from the previous question. And we have the molar volume, which is the volume of one gas at any room temperature and pressure, which is 24 dm cube in this case, yeah? So we have the molar volume also. So now this question says that the volume of 1 mole of any gas at room temperature and pressure is 24 dm cubed. So it means that 1 mole is to 24 decimeter cube, 1 mole of any gas. Now in this case, we have 0.025 moles of carbon dioxide. So what is the volume that that will occupy, right? And now all we do is we equate these ratios. So 1 over 24 equals 0.025 over x. We'll call that the volume which carbon dioxide occupies. And x will be equal to 0.025 times 24, which is a volume of 0.6 decimeter cube. And that is your answer. A simpler way, another way you could use is, there's this formula where the number of moles of any gas equals the volume of the gas over the molar volume of the gas. The molar volume being that 24 we discussed earlier. So in this case, volume equals number of moles times molar volume, which is equal to 0.025 times 24. And that's another way of doing it. Okay, question 9a. 9 gives you a table, this table above, and it 9a asks you to predict the boiling point of bromine. Now, this is just basically pure guessing, and just go along with the idea that there's a gradual change in physical properties as you go along down the group of halogens. So from chlorine to iodine, there'll be a gradual change, like a certain equal amount of change. So just take a number in between these two numbers. That's what I would do. And let's just say that would be about 100, because then it would increase by 70, then increase by an 80 or something like that. Oh, sorry, actually it's minus 35. I didn't see that. So from minus 35 to 184, there is a difference of 219. So you divide 219 by 2. Let's just say if you divide 219 by 2, you'll get 109.5. So let's just say 110. So you just add 110 onto this, and you will get around minus 35 plus 110 would be about 75 degrees. So that would be an approximate, like, in between. So, but the answer scheme says anywhere between 40 to 100. So what I would do is just find like a kind of in between of these two temperatures. It's just a guesstimate. Question 9b says a mixture of hydrogen and chlorine is exposed to sunlight and a violent reaction takes place. The only product is hydrogen chloride. So you got to write a chemical equation for this reaction. So hydrogen always exists as a diatomic molecule, meaning two atoms combined together. And chlorine again always exists as a diatomic molecule, two atoms combined together, and that will give you hydrogen chloride, right? Yeah, so now these two aren't balanced, so the only way to balance this is to put a 2 over there, and so that is your chemical equation. Again, if you have questions, I'm rushing through this because this is really easy, but if you have questions, just post below. Okay, so question 9b2 says that this hydrogen chloride gas, which has been produced, is introduced into separate samples of water and methyl benzene. And then she tests each one with the universal indicator paper. And you have to describe and explain what is seen in each case. Now to do this, I will explain HCl gases reactions in water and methyl benzene. So in water, HCl gas becomes HCl aqueous, which is basically hydrochloric acid, right? But in methyl benzene, this doesn't happen. It doesn't form an aqueous solution, and it just stays as HCl gas. Okay, so that means that no acid is produced in this one, whereas acid is produced in this one. So now we'll use this knowledge to answer the question. So 9b2 asks you, what will happen with universal indicator paper when hydrogen chloride gas is added to water? So the universal indicator paper will obviously indicate that an acid is produced, meaning it will give off the color red. And the reason for this is that what gives an acid its acidity? The fact that H plus ions are produced. So you got to just say that the color of the solution will be red because H plus ions are produced by hydrogen chloride gas in water. And the complete opposite would happen for methylbenzene. In methylbenzene's case, there would be no change in the color of the universal indicator paper, and that is because no H plus ions are produced by hydrogen chloride gas in methylbenzene. And that is your answer.